Hi, I'm Stevie C on The Place to Be. This is a prototype vumeter from ages ago that was inspired by Big Clive's gallium PCBs. It has 10 channels of control for a rainbow Prideflag effect that bounces to music or speech. When used conventionally, the LM3916 upon which this is based can drive LEDs directly without a resistor. One drawback to this implementation is that the LEDs have to have the same forward voltage, otherwise the colours like red and orange clamp the voltage and prevent the others from lighting. In this example, I'm using different resistors for the different LED colours in an attempt to balance them, so I thought it was time to update the design. Also, I wanted something a bit bigger. The first confession of this video is that this is version 2.0, as there were quite a few design mistakes in version 1. This project consists of two PCBs, one for the control and one for the visual display as before, but I've copied the drill holes between them so that they'll clip together with these PCB pillars for a much neater presentation. Everything is based around off-the-shelf parts, from the 12-volt power supply to the LM3916 VU IC and the LM386 mic preamp IC. First up, I'm going to solder the resistors. There's 470 ohm drive resistors for the MOSFETs, and because I'm using P-channel MOSFETs, there's 10K pull-up resistors to hold them in a decisive state. The reason for using P-channel over N-channel is simply because the LM3916 sinks current on its LED pins. There's also some support resistors for the ICs. I've deliberately not put values on the R1 and R2 resistors, because these are the ones that determine the output drive current and comparator scaling. I've seen some people on the interwebs saying they just don't bother with these at all, but I found good results with the randomish values of 1K and 2.2K. I'm soldering the op-amps directly into the PCB to save money on DIL sockets. Because I don't have an IC pin former, I'm kinda just using one side of the PCB holes to gently bend the legs into alignment. I'm using a slab of blue tack to hold the IC in place while soldering. Next, there's a diode to chop off half the audio wave. Sound is inherently AC, but the 3916 needs a DC reference. I've specified an ultrafast diode, but found a regular 1N4007 works just fine. There's also a polarity protection diode. Next is the electric microphone. I've been experimenting with different styles from different suppliers, just because. I've included provision for a switch to select between dot and bar mode. Then we have film capacitors for op-amp bypassing and signal filtering. Now the DC jack for 12-volt power input. Next, it's electrolytic capacitor time. Some of these are very specific values called for by the respective IC datasheets. Others are a mix of low and high values for voltage spike suppression and general power smoothing. I designed the original PCB around these pots I got from eBay, except now I can't find a supplier for them. Luckily, I have these pots from CPC that fit into the 3 right side holes. Finally, I'm soldering in all the MOSFETs. These are rated at 4 amps 100 volts, so I'm in no danger of overloading them. I believe that's the VU processor card, if you want to call it that, complete. So onto the LED PCB. The LED PCB is very similar to a Big Clive gallium panel, except each column has its own positive feed, with 2 common negatives for the whole board. The LEDs are arranged as 12 rows to make up the 6 rows of the Prideflag, and 10 columns for the 10 output stages of the LM3916. I've designed the PCB to accept either a single 10mm LED or 4 5mm LEDs per resistor. With 5mm LEDs, the current will be split between two series parallel pairs. I'm using 10mm LEDs in this build, along with 1 kΩ resistors, which should provide about 8 mA of drive current. This should give a theoretical maximum current of just over an amp. I've spec'd a 2 amp power supply for the project. I'm using my trusty blue tack method to hold the resistors in place, although a strip of LX or gaffer tape will work as well. Now time for the LEDs. I'm using standard diffused LEDs for red, orange, green, blue and pink. The yellow are a bit different though. I don't know how well this shows up on camera, but I'm really not a fan of the standard yellow LED shown on the right. It looks a bit dim and pukey in comparison to me. So what I do is take the standard white LEDs and paint them with this glass and acrylic paint from my local craft store. This gives them a much better yellow in my opinion. The method I'm using to solder them is using gaff tape to hold them in place, soldering one leg first, then leveling them flush with the PCB before soldering the other leg and then cropping them down. Rinse, repeat. With the LEDs soldered, it's time for the final assembly. I'm using this stranded 1 amp equipment wire to connect the LED card to the MOSFET card. As mentioned before, I'm using 2 negative wires as the maximum theoretical current is usually in excess of the 1 amp rating of the wire. In this case, it's only slightly more than 1 amp, but I thought I might as well have 2 return paths. I'm using green and blue color codes to confuse Detective Martin Riggs in future. Robbie Ross will probably still think I'm repairing a VCR though. Now it's just a case of sandwiching the 2 boards together with the PCB pillars. And now to demo it by plugging it into the 12-volt power supply. There's something not quite right here. With the other panels, I get a flash with all channels lit as power is applied, which quickly reduces to reflect the noise level in the environment. Not this slow stepping effect, however nice it looks. I wasn't sure at this stage whether it was electronic noise or something wrong with the preamp, but it still responds to the microphone. Then I noticed something on the processor card. See if you can too. Oops. Yep, that seems to work now. Okay, so confession time. With the first PCB of batch 2.0 built, let's look at some of the mistakes from batch 1.0. The most major F-up is the MOSFETs not fitting into the component holes. It's no big deal, I just used a Dremel with a 1mm tungsten carbide bit to enlarge the holes. I think I know how this happened though. Basically, my laptop died and I moved back to a Windows XP tower to get the PCB design completed and sent off for manufacture. My custom component macros, however, did not get copied across with the project files, so I must have inserted the stock MOSFET one and not thought any more about it. There's still enough copper pad to make a connection though. It is what it is. This is why I'm a technician, not an engineer. One thing about moving back to XP is getting hooked on FreeCell all over again. Oh well. The input protection diode had the wrong component length, so I just angled it up off the PCB like so. So you'll see where I've been experimenting with different styles of capacitor, electric microphone, R1, R2 values, etc. In this one I've just used an off-cut component lead instead of a switch to permanently enable bar mode. As I mentioned earlier, I designed the PCB for both 10mm and 5mm LEDs. The 5mm LED versions take 4 times the time to build because, weirdly, there's 4 times the number of LEDs. Some have all diffused LEDs, and some mixed diffused and focused LEDs, the intention being that they would be enhanced with haze in the pub environment they were built for. This is them doing the do at Dundee Dance event hosted by the Salty Dog. You'll be able to see that while the 10mm version has survived the stress test of sorts, this 5mm version is already having a problem with its pink focused LEDs. I'm not sure if it's the phosphor prematurely failing or what. In my haste to finish one of the boards in time for Dundee Dance event, I realised only too late I'd grabbed a bag of self-flashing LEDs by mistake. In my defence, the LEDs were not marked up as such. So now the bit you all want to watch, the demo. Hopefully you've enjoyed watching this project. If you did, you know what to do. Like and share and all that jazz. Have a happy Pride 2024 and I'll see you for the next video. Thanks for watching.